Right, so welcome to today's online class in Mathematics 1. It's like the good old times during Corona. Unfortunately, we don't have an immediate feedback channel today, so if you have any questions, then please refer to the tweetback. You're welcome to ask any questions on tweetback anytime. Also, if something's wrong with the transmission, if something's wrong with this online format, then please let me know on tweetback and I'll try to repair that problem. All right, I think we're ready to start. So let me first start with a couple of announcements. First of all, I apologize for the short notice. I had to take this online. Unfortunately, I wasn't aware that the Audimax was reserved for that particular date for a different program, different event. And I didn't want to cancel the lecture, and especially not the exercise classes, because I think the current topics that we're discussing are not among the easy ones, to put it mildly. So I didn't want to take away the chance for you to ask questions and to see some more examples for that. That brings me to the next topic on my list, this one here. Next Thursday, so 7th of December, we will again have to cancel classes because on that day, TUM celebrates Dies Academicus, and there will be no classes on that day. So in particular, we'll have to cancel the exercise classes. Good news is I've planned for this in advance. We will still hold exercises for sheet 8 and for the topics that we discuss in the 8th week. So next week, we'll just hold those 1 week later. In particular, there will be no new videos next week. So this is week 7. Next week will be week 8. I hope you all have watched or will watch the videos for week 8 until the end of this week. So we can discuss that the topic next week in the Monday and Tuesday sessions. But for the week after that, we will not have any new topics that we want to discuss. Week 8 marks the last topic of the linear algebra part of this course. And after that, we'll start with the calculus part. I've planned for 1 week in between so that I have some buffer for answering questions, for doing some more problems, for seeing some more examples, and we'll just use that to make up for the lost exercise class on Dies Academicus. So we'll just hold that 1 week later. Also, I'll probably use the Monday of that week number 9 then to make up for the lost class, lecture class on that Thursday. So we have 2 more slots where we can talk about questions. Instead of videos, I'll publish an online quiz on Moodle that will give you a chance to recap some of the topics that we have talked about in the previous weeks. It will probably not be ready by Friday. There's a little more I have to do, so I'm planning to have it online by Monday so that you still have the whole week to take a few minutes to do that quiz. See if you have any questions. If you have any questions, I'll also have a tweetback ready. I will post the URL on Moodle. So if there's any questions you'd like to ask concerning basically everything that we've discussed so far for week 9, then you're welcome to post your questions there, and I'll see if I can answer them then. All right, so again, week 9, we'll spend that with questions, examples, and we'll make up for the exercise class for week 8 that we can't hold next week. We will have exercise classes today. So there will be exercise classes for week 7, but we will have to hold them online in this very same meeting. Just switch to a different format after this course here. And one more thing on my list, the very first point here, just a quick reminder for those who haven't done so, please don't forget to register for the exam. There's still some time, you can still do that, but please make sure to do that before the deadline on 15th of January. Just to recap, you can deregister from the exam up to 1 week before the examination date. So it doesn't hurt to register now, and then if you change your mind, you can always deregister up to 1 week before the exam date. And someone's asking, will a topic calculus start before the winter break? And the answer is yes. We'll have 1 week of calculus before the winter break. I'm sorry, I couldn't plan this any other way. Otherwise, I wouldn't have had enough time left by the end of the semester. And again, I'm planning to have one buffer week, so to say, at the very end, where I'm not doing any new topics. So in case any lecture has to be canceled, we still have a few dates where we can make up for that. And otherwise, we'll just use that for practice and questions. And maybe you can also go through some old exams during that last week. All right, so much about the announcements. Let's do some warm-up next. So here's a couple of warm-up questions. First one, which of these following functions are linear? Let me just share my screen actually so you can you see something? Just give me a second. Might take some time until the screen shows up for you. Because for some reason, switching to the iPad screen takes a long time here at my office. But it will work at some time. At least it used to work. No. All right, so you should be able to see my screen now. My question is, which of the following functions are linear? And I'd like to invite you to answer that question on TweetBack. So for those who don't have the link anymore, it's tweetback.de/ and the code is CNRK. Right, we've got quite a few votes already. Maybe we'll give it 2 more minutes or so. All right, 1 more minute, and we take a look at the results. All right, we're done. So let's see if I can show you the results. Just a second. I hope you should be able to see that screen now. All right, so let's see. Very few of you voted in favor of A, and that is, of course, the correct answer. A is not a linear function, and the reason is this +1 here, right? So in particular, if you, in this case, if you try to compute f of 0, oops, yeah. Maybe let's go through the charts quickly, and then I'll show you the screen, and then I can explain things. It's not good having just one screen. Good. Okay, so A is not linear. You were right there. B is linear, and most of you recognize that. C is not linear once again. D is linear, and again, most of you voted correctly. E seems to be difficult. And again, that is a linear function, so the majority is correct here. Okay, so let's stop that and go back to my iPad screen. Again, that will take a couple of seconds to switch over. Now, I hope you see that now. Okay, so let's quickly talk about this. F. So for A, most of you said this is not a linear function, and you're right. And the easiest way to see this probably is to try to compute f of 0. Remember, for a linear function, 0 is always mapped to 0. And in this case, if you compute f of 0, the result is 1, 0, 0, 0. This is not the 0 vector, and thus f is not linear. All right, for B, most of you said this is linear. And again, you're right. Simplest way to see this is probably to write this in the form matrix times vector. And you know, mappings of that kind are always linear, and it shouldn't be too hard to get that right here. So we need to map from R3 to R2. That means we need 2 rows and 3 columns. And for the first row, we just have x1, x2, and 0, x3. And for the second row, we have 0, x1, 1, x2, 2, x3. And then we can just write it in this way. But multiply this matrix by this vector. So then it's obvious that this is a linear mapping. And then you write that on the left. So A is not linear. B is linear. C, again, is not linear. And there's multiple ways to see this. In this case, it's probably easiest to go for one of the 2 linearity properties. Either take a look at the sum property or at the scalar multiplication property. We've seen similar examples when we've talked about vector spaces, if you remember that. Right, so once again, if you have a linear map, then f of x plus y needs to be equal to f of x plus f of y for all xy vectors. And here you can construct a counterexample pretty easily. For example, if you take x to be, let's say, the vector 1 and then all zeros, and y to be the vector, let's say, 0 and then all ones. If you add those up, then you get the all ones vector. And that means f of x plus y is 1, right? You just multiply 1 times 1 times 1 times 1. That's 1. Whereas f of x equals 0, and f of y also equals 0. So, of course, the sum of f of x and f of y is 0, but f of x plus y is 1. And that's not the same thing. So that means C is not linear. All right, D is linear again. And again, probably the easiest way to see this is to write this as a matrix vector multiplication. I'll leave that task to you. That shouldn't be too hard. And E is also linear for the same reason. You can also write this as a matrix vector multiplication by simply factoring out the x. So you can write this in that way. And then, of course, you can just add up those two matrices, right? So that's 5, 7, 9, and 11 times x. And you're done. All right, so I hope that wasn't too hard. Let me also write that on the border. So this D is a linear function, and E is also a linear function, right? So A and C are not linear, B, D, and E are linear. Good. So that much about this quick warm-up here. I have two more warm-up questions that we can very quickly take a look at. One of those, or maybe both of those, are concerned with the notion of surjective and bijective and injective functions. You'll hopefully remember that. Just as a very quick recap, a surjective function means every point in the codomain is actually reached by that function. So there is some x in the domain where f of x equals any point you want in the codomain. That is a surjective function. And an injective function is one where the values for different inputs also have different outputs. So in other words, no different input values map to the same output value. And the first question is true or false? A linear function f from Rn to Rm is surjective if and only if the dimension of the image of that function is m. So the image dimension is the same as the dimension of the codomain. Is the function that injective in general? Is that true or false? And again, for those who don't remember, here's the tweet back code once again. Just like to avoid switching all the time. Give you one more minute. And meanwhile, I just write down the basic statement here so we can discuss that more easily. All right, quiz is over. I'm not switching screens. You should see that on your devices, the result. For those who don't, about a quarter voted for false, about 3/4 voted for true. And in this case, the majority is right. So this is actually a true statement. Right? Because if the image is m-dimensional and the image is also contained in R to the m, right? That means the image has a basis that consists of m vectors. M linear independent vectors in Rm also constitute a basis for Rm. So necessarily the image is equal to the whole space. Those vectors will always span the whole R to the m. So in fact, it's going to be equal to R to the M. Right, and that means F is surjective, right? Same thing. Okay, and a quick follow-up question. If a linear function, in this specific case from R3 to R2, is surjective, then I claim it's automatically bijective. Is that true or false? That's part 2. I'll give you 1 more minute to think about that. And then once you're warmed up, we'll tackle some more complex exercise problems. Right, 5 more seconds. Okay, here's the result. So a little more than 3/4 said false, a little less than 1/4 said true. And of course, this statement is absolutely incorrect. The reason is pretty easy to see, actually. So if F is surjective, what that means is the dimension of the image is 2. We've just seen that. Right, R2 is 2-dimensional. That's the codomain here. So the dimension of the image would then also be 2 if F is surjective. Well, what does that tell us about the dimension of the kernel? You remember that rank nullity formula, right? The dimension of the kernel and the dimension of the image add up to the dimension of the domain. The domain here is 3-dimensional. So that means the kernel, if you want to have that dimension, that would be dim R3 minus the dimension of the image. So here we have 3 minus 2 is 1. The kernel is 1-dimensional, and that means it does not just consist of the 0 vector, but of more than one. There is a basis that contains one linearly independent vector. The 0 vector is not linearly independent, so it must be a non-0 vector. And all multiples of that non-0 vector are also contained in the kernel. Right, so that means the kernel is not equal to just the 0 vector. There's more to that kernel. And that means there are different elements in our vector space R3 that are mapped to the same value, namely to 0. Right, more than one element of the domain R3 is mapped to 0. Remember, the kernel is exactly those elements that are mapped to 0. There's more than one of those different, and that means F cannot be injective. And of course, if it's not injective, then it can't be bijective anymore. All right. So that's the point here. Just use rank nullity. And in fact, you can see from that I wouldn't even need that surjective property, right? That doesn't really matter. The same argument works if the dimension of f is strictly less than 2. The kernel is always too large. So in this case, the dimensions don't match. The dimension of the codomain is less than that of the domain. And that means the kernel in the domain must always be greater than just the 0 vector. So a function like that, a linear function like that, can never be bijective. Could be surjective, but it can't be injective. All right. Enough about the warm-up. Let's take a quick look at the questions before we go on. Could you please upload your notes after the lecture? Sure, I will upload the notes after my lecture. Why exactly are there more than one elements mapped? Well, the kernel is one-dimensional. That means, let me just explain that, one-dimensional kernel. That means there is a basis that consists of one element. Right? The kernel F is the span of some basis element. Let's call that B1. And as a basis is always linearly independent, B1 can't be 0. Right? Otherwise, it would be linearly dependent. And now that means f of B1 is 0 because it's in the kernel. That's the definition of the kernel. And of course, f of 0 is also 0. Right? Those are not the same. So I have at least two values that map to 0. And of course, any multiple of B1 will also map to 0. How do we calculate the kernel? Well, in this case, there's no obvious way to do that because you don't know anything about this mapping here, right? Only thing you know is the domain and the codomain, and it's surjective. You can't really calculate the kernel with just knowing that. What you can do is you can calculate the dimension of the kernel, and that's what I did. All right, next question. Could you please explain how we get image and kernel of a matrix? We'll do that. I have at least one example where we do just that. All right. Put the dimension. So back to this one. Could the dimension of the image here of F be M? So same as the dimension of the domain. And F still not surjective? And the answer is no. If the dimension of the image is the same as that of the domain, and if the mapping is linear, then of course it must be surjective, right? The image will be the whole codomain, this R to the M, and that means we have a surjective mapping. Of course, not every mapping of that kind has to be surjective, right? But if the dimension of the image is equal to that of the codomain, then it must be surjective. And one quick question about that warm-up here. I also quickly like to answer in part C. You remember that? Why is f of x 0 and f of y 0? So I claimed f of that would be 0, and I claimed f of that would be 0. And the reason is we just substitute the values in here. So for 1, 0, 0, 0, you get 1. Let me write that down. You get 1 times 0 times 0 times 0, and that, of course, is 0. And for this other one, you get 0 times 1 times 1 times 1, and again, that is 0. But if you add them all up, you get 1, 1, 1, 1, and 1 times 1 times 1 times 1 is 1, and not 0. Right? That was the problem here in this warm-up question. Good. I'd say let's just go on, and I'll take a look at the other question I have popped up while you try to find your way through the next example problem. And I've prepared this nice example here. Consider a linear mapping, in this case from R3 to R3, call that F. And F is given in this way. So this time it's not given through the values on a basis as we had last time. It's one of the other ways to define a function. That's just explicitly giving the values for each possible input. Then we also have a basis of R3. this one here. And there's no need to prove there is a basis, just believe me, it is one. Your task is to determine the transformation matrices. And I want those for two different bases. I want them for the canonical basis, which is simply the basis given by the unit vectors. Right, so just to be sure, remember the unit vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's the canonical basis. And I want the matrix representation with respect to that basis, and I also want the matrix representation of F with respect to this basis B here. And then, just as a small add-on, use these matrices to compute the value of F at 2, 4, 3. But the important part is this: determine the transformation matrices F for the basis C and for the basis B. I'll give you a couple minutes. And in a few minutes, I'll publish a quiz on TweetPack asking you for your answers for FC and FP. Mainly try to do FC first, and we'll check the answers before you go on to FC. And as I said, if you have any questions, just post them to TweetPack. I'll write down the URL once again. So for those of you who are already done with FC, there is a TweetPack quiz. If you're not done, don't worry. Still give you some minutes. Here's 4 possible answers. Select which one is correct, A, B, C, or D. I'll just wait until we have a couple of votes before I proceed. All right, maybe let's give you one more minute for FC, and then I'll briefly show you how to do that before we proceed to FB. Right, time's up. So most of you voted for B, and we got a total of 53 votes. That's not bad. And there is a couple of votes for A, D, and C. And the correct answer in this case would in fact be B. So most of you were correct. According to your question, some of you didn't even know where to start. So let me maybe quickly take a look at how you could do that before we start with FB then. All right. So let's do FC first. Remember, F is given as x1 minus 2x2, x1 plus 2x3, and 2x1 plus 2x2 minus 2x3. So if you have the function in this form, the easiest way to get this matrix is probably to realize that this can very easily be written in the form matrix times vector. Remember that I have done this in the warm-up already. So what we want to do is we want to put this in a matrix times vector form, because the vector would then be x1, x2, x3. Right? It's a mapping from R3 to R3. So it's a 3 by 3 matrix. The first row is x1 minus 2x2. That needs to be in the first row of this matrix vector product. So we need to put in a 1 here for the x1, a minus 2 for the x2, and a 0 for the x3. So the first row becomes 1 times x1 minus 2 times x2 plus 0 times x3. And that's exactly what we want here. And of course, it's similar for the other two rows. Second will be 1, 0, 2. Right? There's 1x1, 2x3, and 0x2. And the last one will be 2, 2, minus 2. Right? 2x1, 2x2, minus 2x3. And if you look at that, you will find that this is exactly the matrix FC, because all of this here works in canonical coordinates, in Cartesian coordinates, the ones that you're used to. Right? If you put in the unit vector u1, for example, 1, 0, 0, that means x1 is going to be 1, and all the others are going to be 0. Right? So you get exactly the first column back, because that is multiplied by x1, and the others are multiplied by x2 and x3. So those would be zeroed. And that's exactly the result that we need here. Right? So this is, in fact, this expression, but this here is, in fact, FC. And if you get a function like this, that's probably the easiest way to get FC. There are other possibilities. Let me quickly talk about that. Maybe just one brief demonstration of how you could do that. Remember, one way of getting these matrices is the rule: the columns of that matrix contain the images of the input basis vectors in output coordinates. In this case, input and output bases are the same. That means for the basis C, the columns of FC contain the images of the basis vectors U1, U2, U3, again in C coordinates. So there's no transformation we need to do here. Right, so that gives us the columns where we just have to compute f of U1, f of U2, f of U3 then. F of U1, for example, just set x1 to 1, x2 and x3 to 0 in that formula, and you get 1, 1, 2. And you can do the same with U2, set x2 to 1, x1 to 0, and x3 to 0. And you get -2, 0, 2. And same thing with U3, and you get 0, 2, -2. And of course, that's exactly the columns of this matrix here. All right, so with a function defined like this and the canonical basis, things are usually pretty easy. I hope that helped a little. Let's take a quick look at the question. Why is this example in canonical form? Well, because that was an easy starting point. I mean, we also have FB, which is not in canonical form. So if you want something more complicated, we'll get to that. We'll talk about kernel image later, so I'd just like to postpone those questions for a second. I guess we also take the rest later. If nothing is given, yeah, so here's a nice question. If nothing is given, is f that always defined for the canonical basis? So if I don't define a basis or a coordinate system, and I don't say something like f is given or the vectors are given with respect to that particular basis, then always assume the canonical basis, right? If there's no more information, it's always the canonical basis. Always the usual Cartesian coordinates. That's the default. Anything else will be specified. Okay? So let's move on to FB. The next question is, what about FB? And of course, for those who don't know where to start, you can again use this here. Only this time you need to take the basis B instead of those vectors as inputs. And of course, you need to express the result again in B coordinates, not in C coordinates. Right? And there are other ways to do this. Just choose whatever you like best. Again, I'll have a tweetback quiz on that. Here's some possible answers. And let's see if you can find the right one. Again, the quiz is open, so whenever you have a result, just answer. And I'll just wait until we have collected a suitable number of votes before I move on. So there's a question. Show the question again. Sure, I can do that. Give me a second. Here's the question again. I'll show the answers again in a couple of minutes. Oh, here, just copy the most important points. Well, we have 27 votes by now. So maybe I'll give you one more minute, and then we take a look at how to do this. All right, time's up. Don't worry if you haven't completed it by now. I know that time was a bit short, but I'd like to have some more time to explain that. So here's the result of the quiz. The most voted for was D. You see, there's D here. And that is actually the correct answer. So if you got that, you are right. All the others are not. Let's take a quick look at how you could do this. There's two possibilities I could think of. The one is the one that I just discussed. By using this rule, compute the images of the basis vectors and then determine their coordinates, and those go into the columns of the matrix, right? So for FB, you would compute the results of the images of the B vectors. Let's maybe give those names. So let's say this is B1, this is B2, this is B3. So you would compute F of B1, for example, 102, by using this formula here. And if you do this, you would get, let's see, that is 1 plus 4, that would be 5. So you get 1, 5, and 2 minus 4, so that's minus 2. Right, so that is f of B1. And remember, that is still in canonical coordinates. Right, so if you were looking for this matrix here, input in B coordinates, output in C coordinates, that would be your first column. However, if you want the output in B coordinates, you have to determine the B coordinates of that. And you do that, as we've seen last time, by determining a linear combination of the B's, like that, to represent this vector. And then those lambdas here, those would be the B coordinates, right? So the vector 1, 5, minus 2. Oops. If you want the B coordinates of that, that would be lambda 1, lambda 2, lambda 3. And that would be the column 1 of your matrix. And then you do the same thing with f of B2, f of B3, and you get columns 2 and 3. Right, how do we get 1, 5, and minus 2 again? Hopefully, what I did is I took this vector here, 1, 0, 2, and I substituted it into that formula. And if I didn't make a mistake, that should be the result. If you have a different result, let me know. Okay, so that would be the first column, and then again, you do the same thing for the second and the third column. There's an alternative way that you could use here, and that's the one I would like to show. So we've also seen that once. And that is to use this FC matrix. And of course, that would also work very well if F was defined by some matrix with respect to some other basis. Often it's a canonical basis, but it doesn't have to be. All we can do here is we can use a transformation. If you want this FB matrix, what that means is the input vectors have to be in B coordinates and the output vectors will also be in B coordinates. For the FC matrix, both input and output have to be C coordinates. So what is the relation between those two? Well, on the left, I want to input B coordinates. Here, I need to input C coordinates. So if I just have B, I need to transform them to C first, and then I can input them in this matrix here. So what I need here is a transformation matrix that transforms B to C first, right? And remember, we always read that from the right to the left, basically. That's the process, right? So you multiply something to the right, here or here. That first enters this transformation. The B coordinates in the input are transformed to C coordinates. Then it can be processed by this FC matrix. And that gives you a result in C coordinates. So once again, if I want the result to be in B coordinates, like on the left, I then have to transform that C coordinates into B coordinates. So now I need the reverse transformation, right? From C to B. And that's the relation between those two matrices. They basically do the same thing because it's the same mapping for both matrices, but they work in different coordinate systems. So if I want to have some equation, some equality between those, I need to add the relevant transformation matrices here. And that's the other possibility. I already have this FC. So all I need to do is determine these transformation matrices, and then I can just use matrix multiplication to compute the required FB. Now, how do I get this? Let's look at those transformation matrices. As we're talking about canonical coordinates, one of those is easy to get. And that is this one here. Why is that the case? Well, what this matrix does, let's write that down, maybe BC. So what that does is it takes a B coordinate vector and transforms that into C coordinates. Takes a vector in B coordinates and transforms to C coordinates. Remember, the basis B, let me write that down again, is given as 1, 0, 2, 1, 2, 0, and 0, 2, 1. What are the B coordinates of those vectors? Well, this is the first, this is the second, and this is the third vector in that basis, right? So the B coordinates of that first vector would be, well, take the first vector once, and the second and the third 0 times. So it's just 1, 0, 0. Similar for the other two. The B coordinates of the second vector would just be 0, 1, 0. And the B coordinates of the third vector would be 0, 0, 1. Right? So that looks very easy. Well, that means what does our matrix have to do, our transformation matrix here, for these three vectors? Well, this is a B coordinate vector. The corresponding C coordinate vector is this one. So if I want to transform from B to C, the matrix needs to transform this vector into this one, and this vector into this one, and this vector into this one. Right? If I multiply the matrix by this vector, what that will do is it will select the first column. I multiply from the right. This one will select the second column, and this one will select the third column. So how does my transformation matrix look like? Well, the first column needs to be this vector. The second needs to be this vector. The third needs to be this vector. And that's it. Right? So this B to C transformation is very easy to get. I just use my basis B in canonical coordinates. Right? So that is this transformation. And then if I want the reverse transformation, C to B, what I can do is I can just compute the inverse. Right? I mean, that undoes the transformation, so that is the inverse of this other transformation matrix. You know how to compute an inverse. It's a little work in this case, but maybe let's not do that. I just give you the value of the inverse that you should get if you try that. That should look like this. Right, so that's how we get those two transformation matrices. And now all we need to do is determine that product here. So maybe let's do that quickly. Right, so the desired FB is then, as I said, that is FC, and we need to transform from C to B here, and from B to C on the right. Okay, we know these matrices right now. So B to C, that was this one here. So all we need to do is copy those values here. It's 1, 1, 2, 2 minus 2, 2. Then we know FC, we've computed that already. We should have computed that already somewhere here. Right, here it is. So that's our FC. Maybe I can just copy that quickly. And we also know the transformation from B to C. So this one here was this matrix here, right? So 1, 0, 2, 1, 2, 0, 0, 2, 1. That should be a 2 here. Okay, and now we just need to compute this matrix product. And if you do that, again, I'll spare you all the details here. You should get this result if I did not make a mistake. If I did, I'm sure you'll let me know. So that should be the outcome. And of course, the first way that I presented would also lead to that same outcome. Okay, and here's a question about this. Is the first transformation always made up of the basis vectors as columns, or only because we have FC in canonical form? And the answer is that, of course, this depends on having FC. Let me just take a look at that. Yeah, right. So my argument was, if I want to transform from B to C, this is the B coordinates of these, and these are given in canonical coordinates, right? So I can immediately do the transformation to canonical coordinates by just using these. If I wanted something else, of course, canonical coordinates wouldn't be very useful. Right, so that's why I can just use that as a transformation matrix. You just have to be sure to get this order right. Yeah. Could you show us how to compute the inverse? Actually, I wouldn't like to do that. It's mostly a waste of time at this point. The procedure should be clear. Let me make a note. I'll put that in the suggested solutions. Is that okay? So you can look it up if you, for some reason, fail to do that. It shouldn't be that hard. All right, let's take a quick look at the questions. Which approach of these two is the general one? Well, they both are. So both work. Of course, this approach here, needs to have one of those matrices, right? You either need FC or you need FB to compute the other one. So you need some kind of matrix, but often F is given by a matrix. So that shouldn't be the decisive point here. This approach we have discussed before, by computing the columns of that matrix, by computing images, and then computing the coordinates of these images for the output, and putting those in the columns of the matrix, that always works no matter what, and that even works for different coordinate systems. Same here, of course, that also works for different coordinate systems. You just have to put in the right transformation matrices here, right? So if input and output are different, then here's one for input to this, and here's one for this to the desired output system. And if those are different, then the matrices are not inverses of each other anymore. So you have to compute those two transformations separately. So that probably only makes sense if you have to apply that, maybe not just for one matrix, or if the other way is for some reason computationally very hard to do. Right? So it all depends on how the problem is stated, what is given and what is not given, and in what form it is given. But both approaches work in general. Good. So this was a solution with the coordinate transformation matrix, as one of you demanded. And maybe let's take a look at the other example that I've prepared before we run out of time. That's one of the type that we have just seen. And here we'll also get to talk about image and kernel once again. So hopefully I can also tackle questions about that. Right, so here's an example where a linear mapping is explicitly given by a matrix, right? So you have f of x is defined as matrix times x, and here's the matrix. This is defined with respect to the canonical basis. Here it's explicitly stated. Maybe that should rather be u's here, u1, u2, u3. Remember, you usually write those as u's, not as e's. But if that was not stated, then also you could just assume it was canonical basis. And again, the question here is, given this space is B, what is a transformation matrix of F with respect to the basis B? So same question as we just had. In addition, I'm asking for the dimension and the basis of the image and of the kernel of this mapping here. So maybe let's start with those two. Determine the dimension and the basis of the image and the kernel of F. I'll give you a couple minutes to figure that out. Again, I'll have a tweetback quiz ready for the dimension in just a minute. And once you're done, please just answer those. So do A and B first, and if you complete those and still have time, feel free to get started with D. All right, we have almost 50 votes, so maybe let's give it one more minute. All right, time's up. So let's take a look at the results here. So this is what is the dimension of the image of f? Most of you said 3, and you are correct. And for the kernel of f, most of you said 0, and again, you are correct. And actually, I think this has been an exam question. I don't remember which year, but I remember that has been on the exam once. Let's take a quick look at that, how to solve this. And actually, you don't have to do a lot of computations here. It's actually very easy to see. If you look at that matrix, maybe let's just copy that so I can draw into it more easily. So this is the matrix that defines f with respect to canonical coordinates. We want to determine the dimension and the basis of the image and of the kernel. It doesn't specify in which coordinates, so you're free to choose whatever you like best. And the easiest choice, if the matrix is given that way anyway, why not just use that, right? So let's use canonical coordinates. Now, the dimension of the image of f, you remember that is the dimension of the column space of the associated matrix, so AC here. And that, in turn, is the same as the rank of that matrix. So what's the rank of this matrix, AC? Well, just bring it into row echelon form and then count the pivot elements. And if you look closely, you'll see that this is already in row echelon form, so no need to do any work. Just identify the pivots, and here are 3 pivot elements. So that means the rank is 3. So that means the dimension of the image is 3. Well, F is a mapping from R3 to R3. So if the image is 3-dimensional, then that means the image of F is R3, right? That needs to be the whole codomain because it's included in there and has the same dimension. So if the image is R3, then of course it's easy to use to choose a basis, choose any basis you like, for example, the canonical basis. Yeah, B would also have been a valid choice, whatever you like. As long as you know the image is R3, it's easy to choose a basis. You don't have to do any computations here. Let me just mention, if it wasn't that easy, right? If turns out you need to compute the column space and maybe the dimension is not 3, so you need to do more computations, or maybe it's not already in row echelon form, then maybe you need to do some more work. What you then do is you take the columns of A. In this case, that's 2, 0, 0, 0, 2, 0, and minus 6, 0, minus 1. And you say, well, the image of F is the span of those columns, so I need to compute the basis for the span of those columns. And we usually did this by putting them as rows in a matrix. and then doing row operations to get row echelon form. Eliminate all the 0 rows that you get, and the remaining rows will be a basis. The question pops up pretty often, why do I change here? So I have columns here, why do I change that to rows? And the only reason is if I need to do operations on the vectors, Gaussian elimination operations, I'd rather do this in row form because that's the way I'm used to doing it. You can also do this in column form. That's totally fine. And then you would leave those in column form and do operations in column form. I'd rather work with rows, and that's the only reason that I transpose, right? That's it. Nothing else. And if I'm only interested in dimension, as I am here, then you know that the dimension of the row space and the column space are the same, right? So for the dimension, it doesn't really matter. I can just use this form, and I'm good. If I want a basis, that's when I have to think, do I need a basis of the column space or of the row space? In this case, it's the column space, so I need to work with those columns. And as I prefer working with rows, I just transpose that and then work with rows. Just a matter of taste. All right, so that much about the image. Well, once I know the dimension of the image, of course, I also know the dimension of the kernel. So that's part B, I think, right? Is that part B? Yes. The dimension of the kernel of F is, again, think rank nullity formula. The dimension of the image and that of the kernel add up to the dimension of the domain. The domain is R3, so that's 3-dimensional. So if I solve that for the kernel, then I get the dimension of the kernel is 3 minus that of the image. So that's 3 minus 3, and that's 0. The kernel must include the origin, because f of 0 is always 0. So 0 is always mapped to 0. And if it's 0-dimensional, that's it. That means I also know the kernel, right? A 0-dimensional kernel will always look like this, 0 vector. And now if I'm asking for a basis, it's the only point where I need to remember something more. You might remember that we defined the empty set to be a basis for this trivial vector space here. But that is a convention, nothing else. Yeah, just by convention, the empty set is the basis of that. So that would be the correct answer. The kernel is 0-dimensional, and this is the basis. And the kernel looks like this. Just contains this one vector here. All right. Good. So that solves A and B. And again, in case it wasn't that easy, you could also go ahead and say solve the kernel by hand. You could also say, well, I want to solve this system of linear equations here, right? So I just take AC. I compute row echelon form, and then I solve for x, and the solution set is my kernel. And then, of course, the number of free variables that would be the base. That would be the dimension of the kernel. Right? And from the solution set, you can usually write the solution set as a span of some linearly independent vectors if you do it this way, same way that we always solved linear systems. And that will immediately give you a basis. In this case, you don't transpose, right? You take the matrix as it is, because you want the solution set of this system here as it is. All right, so I hope that answers some of the questions about transposition and solving for images and kernels. Last question, we're unfortunately running out of time here, is that for FB once again. And one possible way to solve this, again, is either using FC. We have that. The matrix AC is AC. And then we just need the transposition matrices here. Right, so we have to compute either that or that, and then use the inverse to compute the other. Or you could again use the approach of computing images of the basis vectors. So that's one approach. The other would be compute images of basis vectors in that basis B, then compute their B coordinates. And those will go into the columns of your matrix. In this case, if you do either of that, maybe you want to try this at home, just let me give you the right answer here. So the correct answer for this FC or AC as it's called in this problem statement here, that should be, hopefully I got this right, should be this matrix here. Let me quickly double check. Yeah, that should work. That should work, and that shows, well, yeah, so that should be the result. You should get a nice diagonal matrix here if you solve for it. Of course, that's not AC, that's AB, thanks. AB and also FB. Yeah, so if you transform this to basis B, that is what you should get. All right, so I see there's still plenty of questions. I'll try to answer as many as I can right afterwards. And if you have any more questions about this topic, I know this is a complicated topic, yeah, so but that's probably as complex as it will get, at least with linear algebra, at least in this semester. So it's kind of peak linear algebra for you. I promise next week will be a little easier, or maybe a whole lot easier even. As I said, I'll have to add something to the suggested solutions. And if you have any more questions about that topic, don't hesitate to post it to Tweetback. And if it's more general questions, of course, we can also use that for our week 9 when we have some time left to answer any questions, not just about this topic, of course, but this will probably be one of the topics that we'll have to discuss some more. So feel free to post your questions. I'll choose some of them to answer in class in this week 9, and I'll try to answer as many as I can online on Tweetback. I'll leave open the Tweetback for a few more days so you can post all of your questions there. All right, that's it for today's lecture class. So we'll switch over to exercise classes in just a couple of minutes. Just stay in the Zoom meeting if you're already here. Those of you following us on YouTube, you're also welcome to join our Zoom. The link is on the Moodle page. Of course, the exercise class will not be broadcast on YouTube because we will be discussing your questions in breakout rooms and small groups with all the tutors, so that doesn't really make any sense. All right, so let me say goodbye for those of you following us on YouTube, and for the Zoom participants, please just stay here. I'll switch over and I'll end the recording.